So we have now both the recordings on, whatever works will be good. Alright, so now everybody is able to see my screen. So yesterday we tried to make up a workflow, but I think we did not save it, or it was giving some error, and therefore the things are gone. But again, so from here you can execute any kind of thing. You can see that. You can even send an email, and you can do Hadoop FS, as in the file system thing. And then you have this generic one. Okay. So all of this can be basically done from here. Okay. So this is quite useful in terms of you don't have to code anything. Alright, so other than this, the way generally in an organization, the way we use Oozie is little bit different. The way we use Oozie is, I'll explain to you. So let's just, so the way we are going to do is you SSH into one of the nodes. Okay. I have already copied the examples from there. So we'll just go through, look at one of the job, and we'll try to execute the job. All right. All right. All right. So this is my home folder. This is my home folder. Okay. So here you can see this project called Oozie examples, and this has been extracted here in examples. All right. So generally, whenever you are building your, the Hadoop jobs, you will be creating this kind of a jar. Okay. And say, let's have a look at what is there. So this is my MapReduce example. Okay, this is one example, and other than this, we have some more uh, code. Say for example, something is written in Pig, something is written in Scoop, something is written in Shell, and so on. Okay, so for example, so this is your project. I mean, it has the example of everyone, but ideally there will be only one. Okay, so here you can see there are these apps where, so basically what you will do is you will create a single folder, and in this single folder you will have the code for all the things you are going to do. In case of Pig, you will put all the Pig script you have written. In case of Hive, you will put all this Hive you want to run, and so on. And at one level above, this is just one recommended hierarchy. It's not like hard and fast rule. And one level above, you have one more folder called src, that is for your Java MapReduce code. Okay, and in the input data you have your input data. Okay, so all of this, after you have bundled it, you will basically move this to HDFS. Okay, so after you have uploaded it onto HDFS, it would look like this. Okay, where did I keep it? I had kept it in a folder called examples. Yeah, here. Alright. So in this, there is at the top level you have pom.xml, which is for Maven compilation. Okay. And it basically says that this is how your MapReduce has to be compiled. Okay. It's not, not required if you're not using Maven. If you are using Ant, then you'll have build.xml here. So one folder contains input data, other folder contains apps, and this apps, if you see, so this apps is little too exhaustive. Okay, too exhaustive in the sense that there is MapReduce code, there is this workflow. Okay, I'll just show you each and every part. So for each of these, this is the jar compiled bundle. I was showing you one folder containing Java code that has been combined together, compiled, and jar has been kept here in this apps. So these apps contain all of your executable code. Okay. So and say in case of pig, and in all of these folders individually, you have one workflow. Workflow dictates that how should your pig job be executed. Okay. This workflow dictates how should your pig job be executed. Okay. Now you can see that there is job tracker, name node. These variables are being picked up from property files. Okay. And these are all arguments that are required to execute your pig script. And this is your pig file. You see, a equals to load input, and so workflow file will be created by you. In case you feel little lazy, what you can do is you go to Oozie editor, drag and drop pig, and out of that you can see what is XML inside it, or you can just take this examples folder and pick up this workflow.xml, and this will work as very good. So the developers have to, whosoever is writing the .pig file can also write it, or Java developers can also write it. Okay. Okay, so yeah, this is created to control Oozie. Okay. So basically it's like saying that please execute my pig script, and before executing the pig script, delete this particular folder, and this is my output folder, and this is my input folder. Okay. Alright. In case your pig script is using some pig UDF, that code will also go into the same folder. And once you have done all of this, you will create, okay, you will have one single, I'll show you. Yeah. So these are one example of each. So we can demo any of this, or we can also write uh, another combined one where we can use these workflows into some other. All right. So here we are. Correct. This is another way of creating a workflow. Now, once you have copied everything onto HDFS, what you can do is you can say things like this. So this job.properties, you have to keep it available locally. Okay, you have to keep it available locally, and okay. So you can see in this particular property file, we have mentioned everything. We have mentioned that this is my name node, this is my job tracker. These are the variables which are being used in all the XML files. So job.properties is the entry point, and this job.property tells everything about our project. So first it tells like where is our name node, where is our job tracker, which is the queue name. Queue name is the one which is used while executing jobs at MapReduce. So we can specify queue name, that's just optional. And this is one folder which we'll be using later on, this variable. So we are just defining variables. And again, here is the path to our workflow application. This is something which is mandatory for any Oozie application. So we mention this path in properties file, and then we execute our job. Okay. So and this path is something which is required. Okay. Now this path equals to dollar name node. And what is name node? Name node is this. And username is your username, current login name. Example root we have just defined here. Example root equals to examples, and apps and MapReduce. So this particular Oozie workflow is what we want to execute out of this. Okay. And output directory is our MapReduce. This is relative paths. Okay. So this is the only entry point we have, and we can basically run it like this. Okay. So we are saying Oozie job, and our Oozie server is running on this particular port, and we've installed Oozie on this particular machine. You can see it in Ambari, and this is our config property file. Okay. This is the only file you need to keep locally. Rest of it you can keep it on the HDFS. Okay. And then you can run it. Now this particular job will start and will get executed here. So yeah, it says it is running. Okay. So it shows it is doing some MapReduce. Alright. Great. Yeah, you can use the Hue UI, but using this Oozie command line is also okay. But I think for most of the beginners, using the web UI is a better idea. But in large projects, what people do is they make a workflow, then they export the workflow from the Hue, and then put it in a XML file, so that the whole process is fairly automated. Right? So now Vikas's question is, so this is another way. All right. Now, so sub projects do we keep in HDFS? Yes. Everything else you need to keep it in HDFS. All the XML files, everything you need to keep in HDFS. All right. So any questions? Was I able to answer your questions, or did I miss anything? All right. So it is doing something, and it might take a little bit of time. All right. Great. So and if you want to execute it elsewhere, or you want to just check instead of running the job, if you want to check what is the status, instead of saying run, you say the job status here. Okay. Ouch. Yeah. All right. So it will keep on showing you the status of the process, or I mean it's not required too much. You can see the status from the portal itself. Okay, so that's pretty much about Oozie. So this example code what you have and this particular slide will actually help you in figuring out how to execute an Oozie job. Alright. So keep a track. I mean, I would say that in case you plan to do it, just have a look at the Oozie examples. It has XML for each and everything, and then you can use either of the XML in your projects. Yes, we have the source code for everything in this. Just have a look at this folder, what we examples folder in HDFS. and you will see that. You can read more documentation here. All right. So all of us are on the same page. Should we start with Mahatma? Great. All right. So when we discussed about Hadoop, MapReduce, Hive, Pig, in all of those cases, each and everything we were designing, as in load this data and compute the average, find this value, that value, all of this. So each and every step was being done by us, and then in case we want to do further analysis, it will be us who will be taking the decisions. We'll have to think of algorithms and we'll have to come up with the strategies. Okay, but in today's time, there are these libraries called machine learning libraries which can help you building the algorithm without you having to understand the data. Okay, all you need to tell these libraries that this is my input, this is the output. Because of these inputs, this happened, and now this is 1 million record of such inputs and outputs. So please give me results. Okay, given an input, what will be the output? These machine learning libraries can help you do that. Okay, so Mahout is one such library which is basically a scalable machine learning library. So lots of machine learning work has happened using R and other similar tools. But when it comes to really, really big data, R cannot handle it. R can at most handle 1 GB of data. Okay, or it all depends on how big the RAM your machine has. Okay, and R is not really designed to handle the the humongous data. Therefore lots of things cannot be done using R when it comes to big data, and that's where libraries like Mahout, MLlib, the one we discussed yesterday on top of Spark, or there is one more library called Spark R, which is R ported onto Spark. So those kind of libraries come into picture. Now, Mahout is a little bit older system, but it still is very useful. It has got a good library of algorithms for machine learning. It is mostly designed after a paper by NG ETL, and the paper was MapReduce for machine learning on multicore. And it started as Lucene sub project but became top level project in 2010. Now, what exactly is machine learning? Programming computers to optimize a performance using example data or past experience. Okay, just the way human does. Human deduces the things based on past data. In the same way, machine learning can also help in that. It's a branch of artificial intelligence, and design and development of algorithms has been it has been used in design and development of algorithms, and essentially machine learning means computers evolve behavior based on empirical data. Okay, so it sounds a little boring, so let me give you a very good demo. How many of you have have played a game called Mario? Anybody has used played a game called Mario? Ramesh has not. Aruna has and Kalyan has. Okay, Vikas has. Okay, so in Mario, you just keep on jumping around and you have to collect all the coins and avoid all the Goombas. Goombas is the that those like turtle shaped things, and you have to avoid them and to reach to the next level. So it's a really interesting game, and yeah, here we go. So if you have YouTube, so you can say things like Mario machine learning. Okay, so this is the one. Okay, let me just give you a copy. This is a very nice video, and I will mute this video. I'll describe in my own words. So what this guy did is it hooked the computer to Mario. It hooked the computer to Mario and let the computer learn by observing Mario. All it told the computer that you can press all of these keys and you can also and observe the game score at this location. So what he did was he basically told instead of he playing the game, he let the computer play the game. The only thing he told that this is the memory of the game and this is the way human observes the game is the same way the computer is starting to observe. The only thing he told is that this is where the results are stored. Okay, and and these are the input points, and so he started the game, and you can have a look at, yeah. So this time he himself is playing the game, but after that, yeah. So now see, initially the computer is playing game really bad. Okay, he's just jumping around stupidly and not even moving, and he just dies of a natural death. Now the computer has figured out that if he moves, then it will be better. Okay. Uh, okay. So again, the computer is stuck here and is not moving. But next time in the next life, he is doing a little better after 3 4 weeks. This is after 3 4 weeks. He's doing a little better, and this time again he'll figure out how to jump on top of it. Okay. So let's see if he figures out or not. Yeah. Okay, so computer is learning based on the inputs and based on understanding the score. That this is something which increases the score and this is something which decreases the score. And so now for some reason it jumps into here. Okay, and let's say, yeah. Now after few weeks, Mario has really mastered the game. You can see that his algorithm has automatically learnt everything. He did not code it. He just coded that here is the score, here's the game, play it and learn by yourself. So computer machine learning library has learnt playing it. Just that sometimes it gets stuck. So he made some enhancements into the machine learning uh, into the library, and it started working really well. Okay, now you can see that. Now what was that? So it basically figured out a way that there is a bug in the game Mario. The computer has figured out a bug in the Mario game that in case it jumps from below and the moment it hits, okay, you can see that it has just become so proficient, just became so proficient. at playing the game. All right. You can see that. See that. So basically, it has figured out how to kill the demon. So what he did was he started moving down when it was jumping on it. So it's exploited the bug in the game, and that is something just marvelous, which people could never figure it out. All right. In the similar manner, he trained his program to play other games. Okay, and was very successful in those. So all right. So given some sufficient amount of data, these algorithms learn by themselves. So was that interesting? So it sounds like a very like the computer behaving like people, behaving very intelligently, given sufficient amount of data. Okay, the fact that today's vision libraries of Facebook and Google are actually competing with humans. Yeah. So was the demo made sense to you, Amish? All right. Yes, it's like a sci-fi movie, but the thing is that it is happening in real. AI has become machine learning has become really good, provided you have data. Yeah. So Aruna, Scala is, I mean, it is not anything that is possible in Scala is possible in Python or Java. It has nothing much to do with Scala. Okay. So it's just that most of the MLlib which we talked about yesterday is written in Scala. So you can do it in Python as well. And this person who has written this algo is actually written in, I think, Java or something. Okay. So the problem is not the programming language like Scala or Python. They are not something this. But what is important is these machine learning libraries are actually doing pretty good. Okay. And yeah. So you can actually use Python also or Java also to program a robot. Like Arduino is that cheap processor which we fit generally into robots. You can program that one using Python also. But Scala is little faster. Okay. Now coming to Amish's question, so was this program you showed used large amount of data? Yes. So what it did was it generated data by itself by playing it again and again. Okay. It generated a lot of data by playing it again and again, and on that basis, it figured out lots of things. Okay. So it played for like 3 4 weeks continuously, which means every 10 seconds it will be like for say how many hours in a week? So 24 by 7, that many hours. And so basically, lucky part in this thing is that it has ample amount of data in which it knew that input and output. Okay, that's why they were able to program such a thing. Okay, like for example, today if you plan to build an automatic robot who can answer to your customers' questions, okay, the amount of data you will get on which you can train the program will be too less, and therefore will not be too useful. Okay. So, for example, we were trying to, at InMobi, what we were trying to figure out from the thumb size, we were trying to predict the age of people. So, at InMobi, we had this advertising platform where, I mean, probably all of you would already be I mean, without knowing, you will be using it. And on that platform, we had this lot of data about the touch sizes of all the thumbs of all the people. We wanted to guess their ages. But since we did not have sufficient amount of input, the test input, we could not use that. Okay. So, all right. So this was a quick demo of a real thing. Is a machine learning example. Now, when we talk about machine learning, there are basically three kinds of machine learning. First one is using labeled training data to create a classifier. So first one is supervised. The second one is unsupervised. Third one is semi-supervised. In supervised learning, you have a very clear data in which there is a clear input and clear output given to you. Lot of training data meaning the data on which you train your program, that is called training data. Training data has a lot of records, and each record has input data set and output data. This is my input, this is my output. So input is generally a big array of numbers. Output is your a single value. So we can always say that these are independent variables and those are dependent variables. So that's what is called a training data. So in case of supervised learning, we have huge training data, meaning because of these things, this happened. Okay, that kind of a huge data we have. Okay, you can imagine that. Let's say there is a manufacturing plant, and you are given all the data about temperatures, that this was the temperature of this valve, this was the temperature of this valve, this was the temperature of input feed, this was the flow of input feed, this this was the date, and this was the climate conditions, and hence our produce was this much. If this kind of data is given to you of every day, you can basically make a prediction that given these inputs, what will be my output at any day. This is supervised learning. Or take a case of email spam. Take a case of email spam in which we know that we already have classified lots of email by using manual means. Okay? And classifying those kind of values is called super. I mean, you have already a clear data on what is input and output. That is called supervised learning. In unsupervised learning, you do not have you do not have labeling very clear. You have unlabeled data. Okay, you in case of supervised learning, given you are already given a labeled data in the form of that this is my spam, this is not a spam, this is a spam, this is not a spam. But in case of unsupervised learning, you are just given an email, full inbox, and are told, can you please organize them into three groups? So those kind of problems lie under the purview of unsupervised learning. Or given say 10,000 news every day, form an automatic correlation between the news the way Google News does. Google News automatically correlates the news and bring them together, so that user, although is seeing the news from all across the globe, but will not see the duplicate news. And in case of semi-supervised learning make use of unlabeled data for training. Okay, so in case of semi-supervised learning, you decipher the labels from say file name, or you basically infer the file, the labels. Okay, so those kind of things lie under semi-supervised learning. Now coming to applications, applications are huge. Application of machine learning are very huge, and basically you can you can do a lot of things what we used to do using manual or clever algorithms. Okay, so we all know about recommending friends, recommending dates, products to end user, classifying content into predefined groups, find similar content based on object properties, and so on. Okay, so these are just few examples, and those are already so prevalent in case of machine learning. So if you keep on showing a characters to the machine and telling that this character is A, this is B, this is C, this is D, and so on. If you have ample amount of data, it will automatically be able to figure out that given a character, it can figure out whether it's A or B. If you sufficiently train it, then it will be able to figure that out. Okay, so there are lots of applications in today's time. The Google Plus and every application you see these days have at least one implication with respect to the machine learning. Okay, so when it comes to tools are very machine learning can be as simple as that given two variable x and y, give based on x please predict y. Okay, so how do you do that, those kind of things? You are giving to a big Excel sheet, say 10,000 records, and you are giving value of x and value of y. So what you generally do is you plot a graph and then you extrapolate the graph. So that's like most primitive form of machine learning. That is the most primitive form of machine learning, that based on x we are able to predict values of y. But the problem keeps on becoming more and more difficult when you have more variables and the graph is not very clear. Okay, when the graph is not really very clear, then it becomes very difficult to predict the values of y based on x. So that is where the various tools come into play. So if you have say few lines of data, you can yourself plot it on the whiteboard and give the results. Okay, so analysis and the visualization of few lines of data, you can do it manually with a pen and paper or whiteboard. If the data starts growing into KBs, meaning thousands of records, then you can use tools like MATLAB, Octave, R, and other tools for processing as well as visualization. But when the data starts growing beyond MBs and into like GBs, then for analysis and visualization, there are two different set of tools. For analysis, you have tools like NumPy, SciPy, Weka, BLAS, and LabVAC. For visualization, there are tools like Flare, MCharts, and Raphel. Okay, but when the data starts growing into gigabytes or terabytes or petabytes, then you don't have the existing visualizations tool for this kind of data. The only way you can visualize the data is by picking a sample out of the whole data and then presenting it. Okay, because presenting a really dense graph does not make much sense to the human eye. And the charts and graphs or any visualization is for the consumption of human eye. Therefore, it doesn't make much sense to plot petabytes of data onto the graph. Instead, you pick up the sample, pick up say a million record and then plot them. Million record is something is okay for human eye, but not beyond million record. So visualization of 100 1,000 billion record does not make any sense. or I mean, even if it makes sense, human eye will not be able to decipher it, as well as um, the tools which are there in the market will not be able to do it. All right, but for analysis, people have figured out the tools like MLlib, Mahout, and Giraffe and GraphX. These tools are great for the analysis of petabytes of data, and this is the area. This is the reason why we studied everything. Okay, because as long as the data is in lower gigabytes, the data can be loaded into RAM and processing is okay. Also, given even if you have 200 GB RAM, the CPU immediately becomes a bottleneck, because these algorithms of figuring out, say, classification algorithms which are classifying the data into groups are actually very complex in the sense time complex. It will take huge time to do the processing. Okay, in our normal life as a BI or BI analyst or as a DBA, the most complex thing we encounter is sorting, which is n into logarithm of n. But these algorithms are n cube, meaning for if something is taking say 1 second, say 2 seconds, okay, something is taking say 2 hours, 2 hours for thousand of record, okay, and in case the record go to 2000, okay, it will suddenly start taking 8 times of time, 8 times the amount of time it was taking for 1000 records, okay. And now you can imagine, so let's just talk about, say, for 1000 record it was taking 1 second, for 2000 it will start taking 2 cube, which means 8 8 seconds. Now, the moment you have, say, 10 records, say 10,000 records, so it will suddenly start taking 10 cube, which is 1000 second, and the graph starts becoming really, it goes really high, and therefore it doesn't make sense to run gigabytes of data on a single computer. It's impossible to solve, and that's where these distributed computing or or multi-core processing combined with distributed computing comes into play. Okay, and that's the role Mahout and MLlib plays. I'm sorry. All right. So today what we are going to do is we are going to do a very simple thing, in which, given the input data, we have to predict the recommendations for them. The input data we have is the name of the persons or the ID of the persons, the ID of movies, and who has rated the movie how much. Just based on this data, we have to give the recommendations. And how do we do that? Okay. The recommendation we have to give is, uh, you know, is based on this. Okay. So we'll use Mahat for this. So this problem statement is clear. Given the past history of various people, we want to give them the recommendations. Meaning, Sandeep liked Matrix and has given a rating 9 out of 10 to Matrix. Sandeep liked Casablanca and has given 9 out of 10. Kumar also liked Matrix and has given rating 9, and so on. Okay? Now you don't have to understand in general how is Mahat going to do it. The way Mahat actually do it is by figuring out which users are very similar to each other and then giving recommendations of one to another. For example, here Sandeep and Kumar are very similar in behavior. They have one movie and their rating is very similar to the same movie. Okay, that means they are very similar, and therefore the recommendation is that whatever movie Kumar has given good rating, the same movie can be given as, as the recommendation to Sandeep. That's why Sandeep, the recommendation output is Sandeep may like Shawshank Redemption this much. Kumar may like Casablanca this much. Okay, so the problem statement is clear to everyone. All right, great. Now, how do we do this? Okay, we'll talk about. Okay, so first and foremost, let's download this data from GroupLens. Okay, and the way you download is you use a wget command, and wget is a very useful command similar to curl. Wget basically downloads a website. So if you have a full website having say 10,000 of pages, wget can recursively download the full website. And so you can say wget minus r and it will download the full website for you. And once you have downloaded it, you can unzip the data, and then you will get something like this. I will show you. Or we can just use Hadoop 2 only. Okay, so Mahat is only installed in Hadoop 1. All right. So I have already downloaded. So let me just download it again. RM minus RF ML 1 million. Okay. So we can simply download this file. Okay, so it is downloaded. And let's unzip it. ML 1 million.zip. So under this folder, you are given these kind of details. There is one file containing movies details, other file containing ratings detail, other one is users detail. So what is important to us is ratings. We are not considering any details about users in this. Similarly, we are not considering the details of the movies in this. So we can say that in the ratings, let me have a look what is there inside it. So we have got user ID. The first one is user ID, then movie ID, and how much this person has rated out of 5, and then at what date. Okay, this is what is there inside ratings.dat. Okay, now the problem is, the problem statement is that we want to feed this to Mahat. We want to feed this to Mahat. Okay, but Mahat expects only 3 columns, and that too comma separated. Mahat expects the data to be comma separated. User ID, comma movie ID, comma rating, and that's it. Okay, how would you convert this data into comma separated? So out of this line, what we are expecting is, so let me just show you in the editor. So what we are expecting is this. Okay, instead of this, what Mahat is expecting is something of this sort. Okay. So what will you use to prepare this kind of data? Anyone? What are you going to use to clean up the data in this manner? Alright, this is what we want at the end of it. Ami says we can use said, Rakesh and Kalyan say regular expression. In what way? Which, how would you use regular expression? Using which tool? Kalyan and Ramesh. Dia says Spark. Okay. So we can load all of this file line by line into Spark and then clean it up. That's what you are saying? Yeah. But then we'll have to again save it and then pass it to Mahat, right? Good. So Kalyan says that we can use MapReduce. Okay. Can we use Pig for this? Okay. Vikas says that he can use Pig for this. Okay. Good. Great. All right. So, yeah. Great. Great. So if we, one way to process this data is by using the Unix command line. Unix command line is pretty straightforward. So you can say, using this, we can say substitute, we say awk minus f, and our separator is double colon, and we are printing back $1, comma $2, comma $3. That's it. Okay, so this will basically print our output. Not like this. Okay, the way we are going to do is this way. Alright, so we are able to do it quickly using Unix command. The problem with this Unix command is when the data is huge, this Unix command will overload our single machine, and our single machine may not be able to do it really fast. Instead, we will use piglatin. Okay, for pig, we have to move this data to HDFS. Okay, which is fair enough because anyway we want the output of this thing as in the HDFS itself. Or once we have moved it to HDFS, we can also run MapReduce without any reducer. We'll just have mapper in which there is no reducer, no sorting happening, and we'll just take the record and replace the double colon with single colon. And there we can use Hadoop streaming and to do the same thing what we are doing here. Okay. So there are multiple approaches. So the various approach is first approach. First approach is export. First approach is using Unix, which is not for big data. Not for big data. Second is using Pig. This is a good approach. Third approach is um, using MapReduce, and it can be either via maybe using streaming. All right, so we can try doing Pig because Pig is probably the easiest one to do out of this, or we can use streaming, that is also straight away. So while using Pig, we can basically say load ratings.dat and using Pig. So okay, guide me. So we need to first copy this file onto HDFS. So what do we do? Anyone quickly? Vikas. So we need to move this file. Yes, we'll say Hadoop fs copy from local. Thank you, Aruna. And great. And we'll say ratings.dat, and I'll just copy it to my folder. Okay. it says file exists. So we can say rm, and I can ratings.dat. Great. Now we are going to copy it to from local. Okay. Generally, moving is far easier and faster. Okay, if you are on the same node in which it's already installed. Now we have copied the data to this location. Okay, let's have a look at it. Hadoop fs ls asgiri. So sorry. Okay, so here there is already a ratings CSV file. We'll just delete both. Okay, we'll say Hadoop fs minus rm ratings. All right, so it's done. Next is that we start our pig command. Okay, and we say load, or before that I'll just change the directory to my asgiri folder. That'll be easier. So now we have loaded this, and let's say we say uh, few equals to rd limit rd 10, and we say dump few. Okay, okay, so I think the dumping was a bad idea, so yeah, I think it got busy somewhere. So after that, what we do is we just iterate over record by record, and that's it. And also note that we have given single colon here because pig storage expects only single colon. If you want to use a regular expression, you will have to use a third-party UDF for that. Therefore, we are just using a single colon, and hence we don't have to worry about splitting the record. Okay, and that's why we are saying 0, 2, and 1, because $1 would be empty. Makes sense, right? Because our actual data is separated by double columns. So, and we are separating it by splitting it by single column, which means that there'll be one empty record. It's taking some time. I don't know why. Yeah. So you can see that fun, then comma, then empty record, then another. This is user ID, then this is movie ID, and this is your rating. Okay, and that's why we are using $0, $1, $2, and $4. Okay, $0, $2, and $4. Now we are saying store this output into this directory. This is a directory. Okay, we can say ratings. So this script is probably very straightforward to you, right? Okay, now once we have done the copying, we have done preparing the CSV file, we can we have already our file will be going to be there only. We can start with we can start with executing Mahat. And for executing Mahat, because we had run it already, there are already those folders created which we are going to use, and therefore we have to delete the older folders. Okay, so our data is written, and we can say tail, we can say ratings, ratings.csv, ls ratings. So you have only mapper, no reducer, you see, and you can say tail. Is tail a command? Tail is not there. We can say cat, and you can see that it has converted our data into comma separated. Alright, now next is that we take the records, we take the older temporary folders which were created in previous run and delete them. Okay, so we say, alright, now let's set our Java home, and now what we are going to do is we are going to run Mahat command, and let's have a look at what we are about to execute. We are saying Mahat, the first argument is the what are we trying to do? We are trying to do item based recommendation, and which algorithm to use for item based recommendation is the next argument we are giving. Okay, then input directory and output directory, that's all. Internally, this Mahat command is going to invoke MapReduce multiple times, okay, to give any results. So it will take some time, so we'll have to have some patience. So once it is done, the result is going to look like this one, where user ID is this one. This user ID will like these movies and this much. It will give us top 20 recommendation for each user. Okay, and this top 20 can be configured to some other number as well. Makes sense to you, right? Any questions here? Okay, so let it run. It will take some 10 minutes to figure out the recommendations on 1 million records. And to do the I mean, for R, it's not actually possible to do the recommendation on 1 million records. It'll take forever. Okay, it'll take some quite a long time. If you don't believe me, you can try it out. All right. No, this is a supervised learning. This is a supervised learning. We have clearly told in the input here, in the input, that this is our user ID, this is our product ID, and this is our rating. So these two, first two records are input, and rating is the output. Okay, now what we are saying is, given these users, can you give me more recommendations? Okay, that is why it is called a supervised learning. So we have clearly mentioned the input and output very clearly. Okay, all right, the other algorithms are these ones, but the difference from one algorithm to another is not considerably huge. The result is going to be very similar, and it's not, I mean, it will be little out of the scores to explain each and everything. Those who are interested, they should have a look at Mahat's manual, and that will uh, give you a good example. Okay. So Ramesh's question is, will you also go over an example of unsupervised learning? So I've not prepared an example on Mahat for unsupervised learning, but if you want, I can show you a quick example of how does it work. Okay. So I'll just give you an example in R. Okay. I hope that will be okay for you. So let's take a case of my big data analytics course. Okay. So also Mario was also not example of unsupervised learning because we had input and output figured out clearly. Okay. Mario was also not an example of unsupervised learning. What I'm going to show you just now is something which you will be able to correlate. I think it's in part 2. Yeah. So let's take an example of this is done in R. This is not some I'm not prepared right away for Mahat, but can be done exactly in the same manner. Okay. So let's take a case of these cars. These are the cars. Okay. These are the cars where we know about these cars that these are the parameters of the cars. Okay. These are the parameters. Okay, every cars, how much mpg, how many cylinders, how much displacement, how much horsepower. We are given a lot of data about all cars. Now what we want to do is we want to compute the grouping between them. Okay, so computing a grouping something like this. Okay, can I make it full screen in some way? So categorizing automatically categorizing these cars into this hierarchy. The cars which are similar to each other, they are very nearby, and the cars which are far away, they are in a different hierarchy. Okay, they are very different. So you can see Merc 280 and Merc 280C are similar. So it has automatically figured out based on this data. Okay, based on input data. Okay, it has automatically figured out that these are the groups or this is the classification. Okay, similarly, given say we are given some data, we are given, let's say, this data, figuring out that if we had to prepare two groups of data, two groups, then we can basically uh, automatically group them. So clustering is another example of unsupervised learning. Given this two-dimensional data, the objective is to find n number of groups. Okay, that is unsupervised learning. All right. So categorization and clustering are an example of unsupervised learning. Okay. So here we could also say that can you just take this data and give me group them into three groups. Okay, and it will give you the results. So that is unsupervised learning. All right. So there are many more use cases apart from there is collaborative filtering, classification, clustering. These are the four general use cases of Mahat. in which collaborative filtering is recommendation, giving the recommendation. Clustering is grouping the items together. Classification is whether something is a spam or not. And frequent item set mining, in which we can give the recommendation at the last point that you may people who bought this also bought this one more. How is machine learning different? I did not get your question, Ramesh. Different from? Same problem we can solve either as supervised or no. So the objective of two is very different. Okay. In one case, in case of a supervised learning, we say that this is input, this is output. That is our training data. Now, here is the input, give me the output. Okay. That is supervised learning. Unsupervised is, here is the data, can you quickly group them into 5 category, or can you prepare a chart of relationships between them? That is unsupervised learning. Okay. So the problem statement itself would tell you whether we are going to use supervised or semi-supervised or unsupervised learning. So if you can just okay, and yeah. So Vikas's point is, if we can get training data, we can do it as supervised if there is no training data set. Yeah. So it generally based on what exactly are we trying to do. Okay. So if we are trying to do the predictions, that all lies into supervised learning. Predictions as in, give me the result for this record, what is the output? That kind of thing is supervised learning. Unsupervised learning is, given these records, just organize them into categories or into a chart. So that is unsupervised learning. Okay. So all right. So let's say we talk about, or you can think of supervised learning as guided learning, as in we taught you just now, can you do it by yourself now? That kind of thing. So Twitter sentiment analysis is not a machine learning problem. Okay. The Twitter sentiment analysis, the one which we are going to talk about, is a statistical analysis problem. But if you are trying to do it using machine learning, say you are trying to do natural language processing, then it becomes a machine learning problem. In those cases, if you try to train it in the sense that this word, this tweet is positive, this tweet is negative, this tweet is positive, this tweet is positive, this tweet is, in that manner, if you're trying to train the machine, then it's a supervised learning. Okay. So we are supervising the computer. In those cases, it's called, where there is a training data set, we say that we are training our machine and then let it figure out, and then it will give us the predictions. In those cases, that is called supervised learning. In case of unsupervised learning, we don't have a generally a training data. We have the full data, and all we want is the output. Okay. All right. So which part, Aruna? Which part you want me to repeat? All right. So unsupervised learning means you are given the records as if you are training a baby, that this is my input, this is my output, this is my input, this is my output. Now, after you have fed enough amount of data to the computer, you will say, now given this input, please tell me what is the output. This is supervised learning, in which we are supervising the computer. Unsupervised learning is, here is my data, can you just classify it into groups? Okay, so that is unsupervised learning. Correct, Aruna, your understanding is correct. All right. So that's pretty much about Mahat's use cases. All right. All right. All right. Is that clear to everyone? What is supervised, unsupervised, and yeah. Should we move on now? So Aruna's question is that what are the top 3 or 4 skills that we need for job or job interviews? For big data developer or data, what is the expectation? From a big data developer, people's expectation is that they should understand Hadoop, they should understand MapReduce, and they should be able to use either Pig or Hive. Okay, so that's an expectation from every big data developer into, yeah. And for data scientists, given a certain amount of data, people should be able to classify them or do the predictions. Okay, data scientists' biggest role is doing the predictive analytics and visualizing it. Okay, although data scientist is really vague and very wide definitions are there, and everybody has their own definitions, but still a general thing which is expected from data scientists is that they should be able to do the predictions. So for data scientist, some people expect R from them. They should be knowing R, and they should be knowing statistics. From a data scientist, they should be knowing statistics, R, and the various algorithms that are available into machine learning is something which is expected from data scientist. All right. People expect R from a data scientist because R is one language which is used a lot in predictive analytics. All right. Okay, so here we are, and all right. And as a matter of fact, some companies basically are teaching only R, which is not fair in case of data scientist. Okay. When we talk about data scientists, they should know statistics and they should know fair amount of details around algorithms. Okay. All right. So yesterday we discussed about Apache Spark. In case of Apache Spark, we were able to handle humongous amount of data in a real time using multiple machines, and utilizing maximum amount of RAM available or maximum amount of memory available. So that was Apache Spark. So because Apache Spark was fast enough, so people found out that the Apache Spark could also be used in stream processing. But Apache Spark was not designed for processing the data which is coming as a continuous stream of information. Before this, Apache Storm has been the de facto tool for doing the stream processing. Okay, if you have say a million records coming in per second, then Apache Storm will not be able to perform as great as Apache Storm does. Okay, but I mean Apache Storm has been dedicatedly designed to handle huge amount of data per second. I mean, lot of records that are coming in per second. So when we talk about velocity in big data, Apache Storm is one such solution. Okay. So the way there are design principles is Apache Storm can be used with any language because it provides you the service bindings, is scalable, fault tolerant, meaning any machine goes down, there is some other machines available, guarantees that your data will be processed, guarantees that no matter what happens, it will be able to process your data. Okay, meaning data will not be lost at any point of time. Maybe one record gets processed twice, but there will be no scenario that one record did not get processed at all, and integrates with the queuing and database technologies, of course. So Kafka and all those queues which we dealt yesterday, it can read from there. So Apache Storm has been for quite some time. Okay, it has been there for real-time analytics, continuous computation, and online machine learning, distributed RPC, and ETL. So there are many use cases of Apache Storm. There are many companies who are using Apache Storm. So if you are building a platform which needs to handle a lot of data, I mean in a real time, then probably Storm will be better than Spark. Okay, if you are building a dedicated system in which you cannot tolerate a latency of 1 second, you have to have latency as in time delay in processing. If your requirement is that my data needs the output I need is in 1/10 of the second, then Storm would be the only solution. While Spark will be good if you are okay with a latency of maybe one second or 2 seconds or maybe more. Okay. In case of Spark, we saw that the time, the batches we were forming were per second, and if you try to do it below per second, the result will not be that great. Okay. In case of Storm, the batches are for very small time. Okay, batches are for very small duration, as in each batch could be of half second or 10 millisecond and so on. Okay, so Storm is great when it comes to really high throughput, I mean high in throughput input, as well as very small batches. Okay, time wise, and that is the only proposition of Storm over Spark. Okay, other than that, Storm has been there at Twitter for quite some time, even before Twitter was formed, and Spark has been created recently and is done at UC Berkeley. Implement One is implemented in Clojure. Spark is written in Scala. The API, everybody provides Java and others, and Spark has also started providing Java and Python and Scala. All right. The only thing is the libraries are not available in Storm. Say that if you have input data coming in and you want to train some machine learning algorithm on top of the input data which is coming in per second. Those kind of libraries are not available in Storm, and therefore you will have to write your own integrations and you will have to do quite a much work. All right. So, and with respect to production and support, if you are taking a call of Storm versus Spark, Storm has been fairly proven since 2011, and now Spark is also okayish proven since 2013. Both are very well supported by companies. In case of Spark, the paid support is not yet available. I'm not sure it is available now or not. While in case of Spark, Databricks, a company called Databricks, is providing the support. And okay, so you can see that from numbers that Storm has run in production for quite some time. However, the Spark streaming has advantages that okay, there is a company supporting it. So on one hand, we have Spark, which is heavily tested over a period of time. On other hand, we have Spark, which is little less tested, but okay is tested for last 2 years. And in case of Spark, you have a well supported company. So generally, in case the thumb rule is in case you are not handling 1 million record per second and your throughput requirement the latency requirement is not below 1, then Spark is great. Okay, if your latency requirement is say 10 milliseconds, 100 milliseconds, then you have to go for Storm. But for rest of the cases, in my opinion, you should go for Spark streaming. If you are okay with saying that per second, if I get the analytics per second, if you are okay with that, then this is Spark streaming is good idea for you. Let's say you are plotting a graph, and on that, on x-axis you have seconds, right? And per second you have to show that how many users are visiting your website. Okay, but then if you have just per second requirement, then Spark streaming is okay. But if you have to show it per millisecond, then Spark streaming may not be great. Okay, so that's a thumb rule. The other reason is for Storm you will have to set up your cluster again, as in case of Hadoop, in case of Spark, you've already set up Yarn, so you don't have to set it up anything, and you don't have to dedicate another set of machines. You can utilize your Hadoop cluster in case of Spark, but in case of Storm, you will have to dedicate separate set of machines. You have to set it up separately. Okay, so in most likely scenarios, my recommendation would be to go for Spark streaming if your latency requirement is 1 second or above. All right, all right, let's take a break of 10 minutes. Okay.